Thank you, Sujru. So it's my pleasure to be here. Thanks, everybody, for coming. I hope you learn a little bit from this talk. Coming from the economist perspective, I know we're going to hear from Susan a little bit later. So between the two of us, at least, we don't feel alone. So I'm going to talk to you about incrementality. Who here has heard about incrementality? Okay, so we got like a third of people here. Who here works in real-time bidding in some way, shape, or form? Okay. So everybody, it seems like there's a good background of people here. So I just like to say that this work is the output of a pretty significant team at Netflix, and so I just want to say thank you to them. With everybody ranging from management that has supported this work. At some point in the next few months, I may have a public paper that I can share, but for now, these slides are what you get to see today. So let's just give you some background as to what incrementality is. And we're going to start by telling you what happens when you don't pay attention to incrementality, or what could happen. So here's a simple example. Here we have kind of the typical graph that I saw when I started at Yahoo. What we do is take the date of the ad exposure, and then we look at behavior of the people who were exposed before the campaign and after the campaign. And pretty much, you could pivot the data several different ways, but this is what would happen. And so everybody thinks, oh, well, look, ads are super effective. There's a huge lift on the day of ad exposure, and it looks like everybody's visiting the website for the ads. Well, it turns out if you run an experiment, the control group looks exactly the same. And why is that? Well, it's actually because ad exposure is selection bias. So we call this activity bias because visiting yahoo.com, which was the the outcome we were trying to drive with the ad, and seeing the ad on the same day, those were both outcomes. So you could have just as easily pivoted the data the other way and asked, does visiting yahoo.com cause you to see ads on other websites? And this is just a spurious regression or a spurious correlation. In the industry, we've at least had citations from people like Majid Abraham, who says that measuring online sales impact of an online campaign is straightforward. We determine who has viewed the ad and then compare online purchases made by those who have and those who have not seen it. So can you imagine if you're typing in a search query like you can't really see up there in the upper left-hand corner that says used Gibson Les Paul. So you're trying to find a guitar. And so, if you're trying to find that, well, you can either get a link to eBay through the search ads on the top, or you could potentially through the ads that are a little bit lower. Or does this laser pointer work? It does. Haha. Okay. Or you could potentially visit these links down here. But so maybe with the guitar, it's not so obvious that maybe the ad is in fact driving additional traffic. But when you type in the keyword Macy's, what in the world are you looking for? Do you think this ad here at the top is actually driving a whole lot of additional traffic that if it wasn't there and you could click on any of these about 8 links, that where would they take you? They're going to take you to Macy's. So the real question that eBay had is, what is the value of these links, and maybe even what is the value of these? And so what they did is negotiations between Bing and eBay broke down, and they stopped doing search ads. And when they stopped doing search ads, what we saw is almost a perfect substitution between the search clicks and then the organic clicks. Essentially a one for one, and then the folks at eBay ran almost the exact same thing on Google, found the same result. So in essence, they had perfect substitution. Not showing ads was just causing people to visit the website through all the organic links that were there, and it really begged the question: should they actually be paying for those search ads? And then maybe you say, well, maybe that was just visits. Well, what about sales? Well, it turns out that you can see here that attributed sales, you can think about these as CPA or click attributed sales. They fall off a cliff in the test regions, but then when you look at total sales, nothing's happening. So maybe like a fraction of a percent's going on here, but they're spending on the order of $50 million, maybe $100 million a year. And that's leading to essentially no impact on sales. So you can think about it as there's a truck driving over from eBay in Silicon Valley, from eBay to Google, delivering truckloads of cash to Google, but not a whole lot's coming back to eBay. And if you want to see this, the paper by these economists is really great. They give some more detail there. All right, so I've given a sense of what happens if you aren't paying attention to incrementality. You're doing correlations that are causing you to make really bad business decisions that can cost you truckloads of money. So when we talk about incrementality, we're really just asking what is the causal effect of an ad. So if we have a control group, we show the ads to the control group. We're reaching, let's say, $1 million worth of revenue, and then if we were to show the ads to the treatment group, randomized treatment group, how much lift would we get? Well, we'd get about 100% or $100,000 lift. So in this case, the incrementality is this $100,000 against the $1.1 million of revenue, or the $1 million of baseline. So in essence, per impression, we're seeing something like an $11 revenue per 1,000 impressions, RPM. But if we wanted to optimize this, what we'd really like to do in a real-time bidding scenario is be able to identify folks like outdoor enthusiasts, recognize that they actually account for, let's say, 80% or $80,000 of that 100,000, and that the non-outdoor enthusiasts are only accounting for $20,000. So in this case, we have roughly a $6 CPM would be break even, and a $1.20 CPM would actually be break even for the not outdoor enthusiasts. So the bottom line is that this would be our valuation. This might be the bid that we would submit in a second price auction. And we would never want to bid more than this, ever bid more than that, based off of the information that we have. Okay, so when we want to estimate incrementality, we got to think about it from like a causal framework, because what happens is we're trying to estimate the causal effect of an ad exposure on purchases, but what happens is that there's these other user attributes that we don't necessarily observe, like are you online today? And it turns out that whether you're online today is correlated with ad exposure, and it's also correlated with purchases. And some of these things we can condition on because they're observable, but some of them are just unobservable to us as in a bidding setting. So what we can do is set up an experiment which is going to perturb ad exposure. It's going to randomize whether or not we decide to win the auction or show an ad, and then we'll be able to identify that. And the nice thing is that if we randomize, we know that that this variable, the randomization, is only correlated. Leads to correlations with X and Y that are or Z is only correlated through X, because we decided to change how we're buying our ads. So we end up identifying that channel, and the nice thing then is that it works. But in the advertising industry, we have all these other targeting aspects where whether or not you see an ad, we have kind of what we would call simultaneity or reverse causality, depending on how you want to think about it. But we have ad exposure leading to purchases. That's what we care about. But we also have all these great retargeting technologies that cause us to then cause purchases to affect ad exposure. And this is, in econometrics speak, this is the worst endogeneity you can imagine, is that the outcome is actually causing the treatment, not the treatment causing the outcome. And so this leads to potentially hugely biased estimates, especially in the world of retargeting. Okay, so, but the nice thing is that when we run an experiment, we actually identify this full channel. So what does this look like sort of mathematically? Well, whenever we always, as economists, always set up regression models. That's, if you've ever talked to an economist, they like linear regressions. We can do nonlinear ones too, but in this case, let's just keep it simple. So we have a simple incrementality model, which just says, beta here is going to be the causal effect of advertising on sales. And down here at the bottom, we can think about a heterogeneous effect, where we can have different weights for different characteristics. So the way we estimate that causal model is actually through instrumental variables, or this is one of the approaches. So in this case, we have a simple second stage, and then we're going to have our randomization, which is going to perturb whether or not we actually show an ad. And because of the orthogonality condition down here, it means that we can this is actually what's known as the exclusion restriction. This says that when you randomize, the error term is uncorrelated. This is the condition for unbiasedness of beta, or consistency of beta. And then we can just estimate two-stage least squares, which is one of the ways to estimate instrumental variables. Okay, but then we want to actually do this in the heterogeneous case, where we're going to have the different weights. So we can still estimate this using all of the causal framework that I just mentioned. All right, so let's do advanced incrementality, because everybody here is like interested in industry. So for those of you who already knew that, now things are going to get interesting. For those of you who didn't know all of that, hopefully I'll have some pictures which will help you sort of follow. All right, so for those of you who work in real-time bidding, you know that data scale is a big pain. It can be really difficult. And so when we wanted to solve the incrementality bidding problem, we didn't want to just like solve it in the academic way. What I showed you was basically the state of the art of like how we understood the problem 2 years ago. And so what I want to show you now is like the advances that we made over the last year and a half or 2 years towards actually making this something that could be viable and scalable for real-time bidding. If you want to know why Netflix is interested in this, it's not because we show ads. Who here has ever seen an ad on Netflix? That's a trick question. I won't answer it though. But yes, we don't show ads, and I hope we don't ever, just because ads are great. But anyway. So the hope is that what Netflix wants to do is, because they spend about $500 million a year on advertising to acquire new subscribers, we want the rest of the industry to actually know about incrementality so that we can start buying ads in a way that actually drives value for our business. We don't want to be like eBay for a decade, spending $50 million a year in excess that's not actually driving any value. And so we're working hard towards ensuring that everybody has kind of the way of thinking about the problem that we want you guys to design and build. So feel free to reach out to me afterwards if you want to know more details. But the thing is, we were actually able to make like reasonable progress on this in a way that actually makes it scalable. So a couple of just the key insights that I think are worth noting here is we've developed something called Scalable Sparse IV, which we think is the type of thing that can be estimated on a single machine. For those of you who know Benoit Rosticus, I've been working with him towards developing this. He's responsible for some of the work that was done at Criteo and at AdRoll. And we have a couple of other techniques here, like the Hausman causal correction, which makes incrementality actually viable within a prediction and causal system. So anyway, but the key thing here is we're still working on getting critical mass of advertiser demand so that we can get this type of technology developed and enough support to make it viable for businesses. All right. So how do we want to think about advertising? So I want to think about it in continuous time. So we're gonna have an equation like this, which is we're gonna look at the rate of conversions coming in, and we're gonna look at how the baseline A alpha of t, we're gonna look at that over time. So think about this as the baseline. For the most part, I'm not gonna talk a whole lot about the baseline. But what we're gonna talk about is incrementality. So incrementality would be that at time t equal 2, we're gonna have a spike in behavior because we showed an ad. So this is what we hope is going to happen. We show an ad, people respond, we see a change in behavior. Maybe the shape doesn't look like that. Maybe we want to adjust it by some factor like this, and instead we want a pretty little curve like this. So we can add additional kernels to the features that within the functions, and that'll allow us to identify the causality over different horizons. So this is the curve that we're going to work with. And we also have to deal with multiple impressions. So suppose we have a second ad. We now need to think about how we're going to model the incrementality over time. The second ad's effect can be dependent on the presence of the first ad. That's what you would want in a continuous time setting. We can have the ads, even the size of the ads and even their shapes. They can all vary as a function of characteristics of the ad. And so the nice thing is that this is essentially a full-blown valuation model that gives us very rich ability to model features and heterogeneity among advertising. Okay, but what we're going to observe is data that looks like this. Like the data we observe doesn't tell us whether it's incremental or not. We need to use a model in order to establish that. So one of the things we'd like to know is what share of a given conversion is attributable to advertising. So if a conversion happened at this moment in time, it would be 70% incremental because the ratio of the orange area to the gray area to the total area is 70%, and 30% of the conversions are non-incremental. This is our best expectation based off of the causal modeling. The nice thing is because we have the overall model, we can also break down the incrementality by each of the impressions. And so you can see it a little better here, that the second impression is responsible for 31% of the incrementality of the conversion, and the other one is responsible for 39% of the conversion. So this gives us a nice way to break down the incrementality by impression, which is essentially what we need to do. We need to know how much contribution did this particular impression give towards driving that particular conversion, so that we can value these things. Okay, nice thing is that if we have another conversion that comes through for the same user, within the time horizon that the first two impressions have happened, we actually get to observe some additional incrementality share that we can give it. So basically, this is each impression's total causal attribution credit. So this is attribution, And now let's move on towards establishing how we would estimate the model. So this is not ad hoc. We actually need to go to the data. So each one of these stars represents a conversion. You can think about having a distribution of conversions and a distribution of impressions, and then we need to estimate this instrumental variables model. And so this is going to lead us to the bids. And the key thing here is that these areas I've been showing you are the incrementality. So the area is the incrementality. So we can quantify the valuation for each one of the ads by just estimating the area. So here's an pretty animation. Everybody likes animations, don't they? So what this shows is that over time we're going to go from having only expectations of incrementality towards realizations by actually observing the conversions. And so at the very, you can imagine that maybe only 1 in 1,000 impressions is going to actually have a conversion event appear in some of our sparse settings, and then the rest of the impressions are going to have a very small amount of residual incrementality that will diminish to 0 over time. An impression that happened, let's say 3 years ago, its incrementality is completely diminished today, and that's what this graph shows, is that with time, the incrementality that we're looking at for a given impression diminishes. Okay. Was that a fun graph? Sorry, it took me way too much time to create these figures. All right, so I'm just going to skip through this. We already talked about that. One of the nice things is that this combination of valuations. So note here, this function is actually interesting because it gives us the incrementality share or the credit for a given impression that we've observed, and then it gives the portion that we have yet to observe or have yet to realize that has not been observed in our data. And the nice thing is that we can take this incrementality, so this sort of expected incrementality, and we can just throw it into any of your favorite attribution model, into any of your favorite machine learning technique or humans. They can look at it, and then either the machine learning algorithm or a human can make a decision based off of this number at any point in time. Meaning we don't have to wait for the campaign to end. We don't have to wait for the impressions to fully amortize. We get a value, a total incremental value right at the beginning. So these numbers here move all through time, and we're able to see how much incrementality each impression should have driven up to that point, and we also get to see how much it actually has. So in some sense, the expected incrementality of a well-calibrated causal model should not vary over time. Meaning, if you were to put this stuff in a dashboard and you were to start buying those ads, the number, maybe it'll wiggle around a little bit with variance, but the actual numbers that are in the dashboard shouldn't really change. If your model's biased, that's exactly what happens in online versus offline machine learning tests. Sometimes your offline test says that it should be giving you one answer, but then you go online and it gives you a different answer. That's because you're not using a causal framework. So, okay, next step. All right, now we want to estimate a model in incrementality model in continuous time. Why do we want to do continuous time? And it's not just because we want to be fancy and we want to use things, want to say continuous time panel data or have fancy plots like this. It's actually because it matters in the industry. So I'll tell you why it matters in a minute, but you have to hear what it actually means in the first place. So in the world of econometrics, we tend to construct models that look like this. So YIT, so we're going to look at kind of a blockwise set of time. And then we're going to have blockwise aggregation of impressions. But the thing, and we know how to do causal modeling really well in this type of framework, but we don't know how to do it in the typical machine learning setting like real-time bidding, where you take a given impression or a given conversion and you take the state of the user at that time and then try to predict it. And so, so in order to get these causal frameworks to work well, we actually need to go towards the machine learning paradigm of sampling at every kind of, wherever you want in time. And what the problem is if you do that, you're going to increase computational cost by a factor of 3.6 million, going from milliseconds to from hour to milliseconds. And so this is one challenge we ran into. So the continuous time data helps us solve that problem while still retaining all of the causal frameworks that we want to use, that we know as economists, as econometricians, how to use. So the concept of downsampling is actually key here. It turns out that if you think about trying to estimate how much area is in these curves, you can think about sampling just the point, all the points, at granularity all the way down until you've basically done a Riemann sum. Or you can just sort of approximate that to first order. And it turns out that in our example here, suppose we have 1,000 positives, y equals 1, and sample 10,000 negatives for y equals 0. Then we have this constant ratio of c. But it turns out that the formula for the variance of our estimates is equal to roughly proportional to 1 plus 1 over c. So we can just basically, we don't need to do that 3.6 million calculation. We don't have to make our lives computationally intractable. We can actually just do this trick. So we're going to use downsampling, but we're going to do it in continuous time. All right. So the intuition there is a little bit of a catch here. So for those of you who've ever done a classification problem, you know that if we want to get the basic expectation in a classification problem, we're essentially trying to just compute the ratio of positives to negatives, or ratio of positives to overall. So in this case, in our continuous time model, we want to basically estimate the expectation of y per unit of time. And so what we'll do is we'll take the number of positives we've observed, and we're going to take the number of units of time times the number of people number of users in our sample. And in the standard classification setting, your data would look something like this. And so you'd then, if you were going to do a least squares regression, in order to generalize this a little bit, you'll have in the denominator the contribution of positives and negatives, and in the numerator you have positives and negatives. But but if we're doing a negative, well, that's 0, and so our equation actually reduces to just the contribution in the numerator, again, which is just this y equals 1 idea, and the contributions to the denominator, which are coming from both the positives and the negatives. But in continuous time, if you start thinking about it, the actual positives are occurring on a set of measure 0. It's basically the positives only occur at, like, let's say 1 femtosecond or something like that, and then everything else in time is a negative. People don't convert in continuous time. I wish they did, because then we'd make tons of money. But the reality is that you're going to observe a sparse set of a finite number of these conversions that you're going to count. So what do you have to do? Well, in continuous time, we're going to have an equation that looks like this. But the funny thing is, as this part, the negatives, are going to start to account for the entire denominator. So what we actually need to do is this is only one approach to solving this problem. But what we actually need to do is augment the data with these things that I'm going to call a double negative. Exactly why you have to do this, I'll leave you to sort of think through. But I'll prove to you that it actually works in just a second. But the idea is that by augmenting the positives with these double negatives, we're able to offset the contribution of the positives to the denominator, which actually introduces selection bias. So basically, you can't do the same thing you're used to doing, because in continuous time, positives only happen on a set of measure 0, and so you need to ignore them when you're computing the actual gradients. So the nice thing here is that when you go through all of this effort, it turns out that the expectation of this function is equal to beta. So we actually have an estimator that is in fact going to estimate our causal effects properly. Okay, I'm going to skip through this because everybody else thought it was confusing. But the idea is that if you're going to build your data set, you're going to build a data set that looks like this. You're going to do the typical thing. I'm going to have my negatives. I'm going to compute my regressors at the moment in time when I sampled the negative. And then the weight I'm going to use is this particular sampling weight that I showed before. And then the positives, I'm going to do the typical thing where I'm going to evaluate the regressors at the moment at which the conversion happened. And then I need to augment it with this additional set of double negatives in order to avoid the selection bias from having selected the positives and then selected the negatives uniformly. All right. So just to prove to you that this works, we got 2 lines on our curve. And the red line is the line that happens if you don't use the double negatives. And the black line is the line that you get if you use the line that does have the double negatives. So it's actually something that I thought was really interesting, and I felt like was like a real breakthrough about a year ago when we figured this out, that this is how we can actually do a continuous time panel data. This is how we're going to solve the next problem. So what is the problem? Why did we need all that? Well, in the world of advertising, we have this thing called negative targeting, which I already mentioned. Negative targeting, if you were to construct a typical panel regression model that I mentioned before, you're going to start collecting data within sort of time blocks. So every one of your features is going to be a sum within a unit of time. And the problem here is that if you have feedback loops that are occurring on a time scale that's shorter than the resolution of your time window, well, that's going to introduce endogeneity. And just here's a simple example. So in this case, the user A and user B are essentially identical, except for the fact that one of them randomly is going to have converted before the third impression. They're going to have converted at this moment. And so this user is going to see 2 impressions and will have 1 conversion. However, the person down here has 3 impressions and 0 conversions. And so the coefficient that is estimated from this model is that the causal effect of an ad impression is -1, meaning the ads are actually harming signups. The model is not saying that. The model is positive everywhere, which means we have a severe bias. So this is what happens. This is one of the mechanisms through which we have endogeneity, or this failure of the least squares condition of exogeneity. Okay. All right. So this is an illustration of what happens as we progressively go from a panel data set to a continuous time data set. As the time resolution shrinks, you'll see that the numbers here on the right get really close to the truth. But when the numbers are really big, these numbers are just complete garbage. And this is not like a sampling thing. This is actually like a structural bias in the model that you just wrote the model down wrong, and you collected your data wrong, and you you basically absorbed the feedback loops that are going on in terms of the negative targeting. So basically, the moral of the story is negative targeting, if you're an econometrician, is like the worst thing you can ever encounter in terms of endogeneity and feedback. But there's a way to solve it in our setting. So here, I haven't even used instrumental variables. This is just like straight up panel data. Okay, but now we're going to get to the point where you have to solve actually a little bit more difficult problems. So this is the curve that we were looking at before. This is the curve that probably actually happens in reality. So suppose I'm Netflix. I'm showing an ad on RottenTomatoes.com, and it's for House of Cards. When people visit RottenTomatoes.com, what's going to happen is that they're going to see they're going to get treated for Netflix at that moment in time. They're going to learn about House of Cards, and they're going to decide, hey, maybe I actually want to go watch that show, so I'm going to go sign up for Netflix. So then the question is, well, did the ad cause people to visit Netflix, or did RottenTomatoes.com House of Cards webpage cause people to visit visit Netflix and sign up? And so we don't want to be paying for people to visit Rotten Tomatoes when in fact we can get that for free by not paying. So the real question here is how do we deal with this? I wish it was that easy. Turns out that what we really have in most situations is that activity bias thing I was telling you at the very beginning, which is typically it's going to look like a run-up before the impression is shown, because people are visiting other websites and having other actions that are related to, say, movie watching, leading up to that. And so there's a chance that they're going to go visit Netflix instead of visit Rotten Tomatoes. And as a result, it's almost impossible to establish what the baseline is in this case. All right. So then you start adding multiple impressions onto this mess, and now you're trying to estimate some horribly complicated function where you don't even have a baseline. Your baseline estimates are just are basically intractable. Okay, so what would be the ideal? The ideal for those of you who's here ever worked with propensity score modeling or of some sort. Okay, so this is propensity score modeling. In an ideal world, you can basically say, well, I can condition on what the baseline should look like, because conditional on everything that I observe, I'm going to win and lose the auction randomly. I don't believe in this. This doesn't happen because but if it did, this would be our model, and then we would be fine. We wouldn't even have to worry about anything, because ad exposure would be conditionally random. But what actually happens usually is non-random non-compliance, because winning the auction is not random, meaning we win different types of people than we lose. What you typically will happen is the baseline is going to move. It may be inversely correlated, or it may be positively correlated with winning and losing. In this case, I've shown it's positively. So when we lose an auction, the baseline falls. When we win an auction, we win the auction for people for whom the baseline is high. This is bad. In this case, we can't interpret our estimates as causal. How do we solve this? Well, instrumental variables is the solution, I would say. in that, because what we essentially are going to do is we're going to randomly decide to lose. So we're going to enforce our own random non-compliance, and we can engineer this by randomizing whether or not we show the ad. And so for those of you who have who've read my Ghost Ads paper, this is all the Ghost Ads is all about, but now visualized in a real-time bidding context. And you know, the next extension of this, which you know sort of is quite straightforward, is that we're going to use ghost bids instead of ghost ads. In essence, we're going to record the bid we want to submit as a ghost bid, and then we're going to randomly decide to not bid. And by doing that, we're able to simulate. Basically, we're able to establish you know, a consistent baseline for those auctions where we wanted to try to win, and then we can come back and construct these predicted ghost ads. All right, so just to convince you that this works, for all of those of you who really like you know, model fit or out of sample prediction error problems, instrumental variables gives you a few challenges here. Which line fits better, the black one or the red one? Any votes? The red one, right? The red one looks great, doesn't it? Well, that's least squares. Well, you know, it turns out that it looks like it fits great, but then when you actually you know, reposition it so that we're focused on the incrementality estimates, which is the part of the equation we actually care about because that's what we're going to use to bid, it turns out the red one's terrible. The red one is sucking up a whole bunch of that endogeneity I was telling you about, and it's actually leading to basically overstating the bids and or mispricing all across it. So this is really great. Instrumental variables works. It can give you the correct causal estimates. But it's going to do a poor job on estimating this baseline because, well, you weren't randomizing that anyway, because you weren't trying to figure that out. We only want to estimate the causal part. All right, so I'm down to, I think I have 10 minutes, 5 roughly. Okay, so now this is the interesting part. For those of, if you're already bored, now let's actually talk about making this production ready. So the requirements for one of these systems to actually make any sense is, one, it needs to be causal, and this means that our predictions of the valuations needs to be unbiased or at least consistent in some way. It needs to be predictive, which means we're going to minimize some out of sample prediction error. And why do we want to do that? Well, so we don't submit crazy bids of like, you know, $1,000 CPM when we have a lot of noise in our estimation. Causal modeling is notoriously noisy, notoriously bad for being noisy. And so, you know, we need to deal with this problem. It needs to be scalable. For those of you who've ever estimated a causal model, sometimes they have like an extra layer to them. We need to solve that. And then finally, we need to make sure it's efficient, meaning we want it to be statistically precise as possible. And so how are we going to do that? Well, let's see. So in the world of instrumental variables, we know how to do this. It basically just boils down to choosing some transformation of our instrumental variables. Our instrumental variables are the randomization. And so in this case, you can think about the G as being the ghost ad. It's trying to say, when are we going to win the ads, and when is that going to lead to additional ad effect versus not. And so we basically are just trying to maximize this inner product. And so if we maximize the inner product, it's going to maximize this inverse part of the variance, and in essence, minimize the variance of our instrumental variables estimator. So none of this is like super deep. This is stuff from like the 80s. But you know, it needs to be tractable. So some of the things that are from the 80s aren't tractable, like computing inverses when we start to get to scale. Okay, so I'm going to introduce you to a concept called the Hausman test. Who here has ever heard of the Hausman test? Okay, we got like 3 people in the room. Okay, so if you take one thing away from this talk, I think you should take away this concept of the Hausman test and the machine learning extension that I'm going to call the Hausman penalization. So the Hausman test is basically says, well, we have a causal model and we have a correlative model, and it says, are they different? And so this is essentially just an F test. We're going to say, is my correlative model and my causal model different? Because if it turns out that my correlative model looks, gives me the same predictions, within statistical error of my causal model, I should just use the correlative one because it's going to have way better predictive power. It's going to have smaller mean squared error. It's basically going to be better in almost any way you can imagine. And we as economists, we're nervous about doing this because we care a lot about, generally about being unbiased or consistent in our estimates. I would say that's good for economists. Maybe not so good for practical engineering applications where we really care a lot about the variability of our estimates. But in this case, it gives us the ability to test this. So if you're an astute machine learning student, you might say, hey, that kind of looks like an L2 penalization here. So what are we going to do? Well, we're just going to throw an L2 penalization at the problem. So now instead of minimizing, so this is the IV objective function, or the GMM, generalized method of moments objective function. We're going to take this, we're going to bolt on a Hausman penalization here, which is essentially going to give us a scalable set of Hausman tests. So if you have 1 million features that you're using for valuation, this is basically going to boil down to doing something like 1 million Hausman tests. And, that's kind of nice because now we don't actually have to do them, and we don't want to be frequentist anyway because, we don't like frequentists. But instead what we're going to do is estimate. So we're going to have this correlative model, which is the ridge regression, which is essentially going to be much more precise than the causal model. And then we're going to essentially estimate the causal model with a penalization towards the correlative model. And this is going to help us improve our predictiveness. Instead of having a crazy noisy estimate, we're going to say that, well, if the causal model either has too little power, meaning we haven't experimented enough, or it doesn't look any different from the correlative model, we're just going to use the correlative model because that's kind of the status quo anyway. So in a machine learning system, this totally makes sense because typically in these machine learning systems we're going to have data, we're going to train some model, and then we're going to go make a decision. But you can see this is like a terrible feedback loop. This is just like the retargeting example I was showing. And so this suffers from, in the world of economics, we would call the Lucas critique, which is as soon as you have changed your decision, you've changed the data generating process. When you change the data generating process, the distribution of data changes. And so you want a model that's going to be consistent, sort of consistent through this whole feedback. So what we're going to do in a practical setting is we're going to introduce a causal correction to this model. And so that's what the IV model is going to be. And then we're going to bolt it on to the model, and we're going to make a better decision by doing this. And that's what essentially the Hausman penalization is doing. So, the way in a practical case, when we want to do this, we might use to estimate two-stage least squares, which is one of these estimators for causal models, for instrumental variables models. We're going to use something called the control function approach to, and the really elegant thing about the control function is that it has this little parameter new hat. And it turns out that there's a way to write the Hausman test where you use new hat, and then you just test whether or not the beta on new hat is equal to 0. And in a frequentist case, this is really easy, really convenient. And so this is that's one of the key observations. But the nice thing here is that because we have a regressor here, well, why don't we just put some L2 penalization? Because when we send the coefficient on this to 0, it goes back to the correlative model. And so this is the key observation, is that the beta here is just the difference between our correlative and causal model. So instead, we're going to use maybe ridge regression. We're going to L2 penalize, and that's going to give us this Hausman penalization in a practical engineering situation. So I haven't had to do anything here in order to estimate this model that you can't do in R already today, or in any statistical package. All I've done is run like 3 regressions and then impose an L2 penalization. So like everybody here, if you've understood this talk and you have an instrument, you actually have a randomization, you would be able to implement this in some way. It may not work exactly how you expect it to, but in principle, there's nothing that you need to actually go code up yourself in terms of core packages to make this happen. All right, one of the challenges here that's not scalable because at least if you had sparse x's, you now have a dense new hat. That's bad. Your data is going to blow up on you, and it's going to be a mess. And so it's beyond the scope of the talk today, but there's a way to solve that problem, and maybe there'll be another paper on that. All right, just to prove that this works, back to our graph before. IV works, OLS doesn't. This is what it looks like as you increase the sample size. Ideally what would happen is as you gather more and more data, the Hausman causal correction estimator is going to converge to the causal one. But initially, it's not going to accept quite as much crazy variability. So it's going to start out in your OLS case. It's going to accept bias in exchange for lower variance, and then it will converge for you. So This is kind of a nice feature. It can lead to much better performance than you would have with the standard causal model. All right, and here's just examples showing the variability and showing the blue line converging to the black line, and always generally being less biased than the red. Okay, so there's generalizations to this, but I'm pretty much out of time. You can think about, you don't need to use linearity. You can use other exciting models too. So it's just concept of derivatives and combining, the complexity of the model that you have. All right, yeah, I already ran out of time. Let's see. All right, we're going to do this one just to give you the final picture. So this will be essentially be my conclusion. So the concept here, just, if you take one picture away, take this one. It's that in what we're trying to do is essentially think about these three sets of parameters. We have the correlational model, the causal model, and then we have our prior of 0 that maybe complexity, maybe dimensionality isn't so important. So machine learning lives on this side of the graph or of the triangle, and we're going to get some predictive beta out of that. And we're going to try to balance off the trade-offs between overfitting and underfitting. And then over here on the right, we're going to have these regularized bandits, which for those of you who've worked on bandits and tried to throw it into elastic net or whatever penalization you want to use, this is it's kind of the same concept except applied there. Susan would have a lot of things I think to say about this as well. But one of the classic things that happen here is you don't have enough exploration data. It tends to be undertrained. It's going to be noisy. Sometimes it's going to be a pain to deal with to gather the data because you have to gather it, gather enough, and then run all of your offline experiments. The world of econometrics lives across the top. We don't usually think about regularization, at least we haven't historically. We're getting there. And we have this Hausman test, which allows us to bridge the correlational causal worlds and make a decision about it. And so now I'm saying let's just use a Hausman penalization on this. And what we're going to do is start with our predictive model. We're then going to use that as a prior for our causal model and do a penalization against that difference instead of the 0 difference down here. And then, by fitting some regularization parameter there, we're able to get our beta star, and that gives us our sort of our ideal causal estimate. So here's a really sloppy equation, which kind of illustrates the intuition, but isn't quite correct. So, all right. So anyway, I think I'll leave it with that. And thank you so much for your time. And I guess maybe is there time for 1 or 2 more questions? Okay.